Welcome to my channel. Today, we're going to discuss one of the most impressive AI papers to drop recently, Kimi K2.5 by Moonshot AI. This is a model that doesn't just specialize in one thing. It achieves state-of-the-art results across text reasoning, vision, coding, and agentic tasks all at the same time. Think about that for a second. Most models are struggling to be the best in even one area, and Kimi K2.5 is topping leaderboards in all four. We're talking scores like 86.7% on AIM 2025 for math, 46.7% on SWE-Bench for visual reasoning, 75.6% on SWE-Bench for software engineering, and a 17.8% improvement on BrowseComp for agent tasks. And the three core innovations driving these results are Vision RL, cross-modal transfer, and something called Agent Swarm, which we'll break down step by step throughout this video. So, how does Kimi K2.5 actually work under the hood? At its core, it combines two major components into a unified architecture. First, you have a mixture of experts' LLM backbone, which is the text processing engine. This is where the heavy language understanding happens. Then you have Moonvit 3D, which is a specialized 3D vision encoder. What's clever here is how these two streams merge together. Text tokens flow in from one side, image and video tokens flow in from the other, and they meet at a unified representation layer. The mixture of experts architecture means the model can selectively activate different expert modules depending on the task, making it both powerful and efficient. This fusion is what allows Kimi K2.5 to handle text, images, and videos in a single forward pass, rather than needing separate models for each modality. Now, let's zoom into Moonvit 3D, because this is where the vision magic happens. Traditional vision encoders process images as flat 2D grids. Each frame gets analyzed independently, which means if you're looking at a video, the model has no idea that frame 5 is related to frame 4. Moonvit 3D takes a completely different approach. It treats images and videos as 3D volumes. For a single image, it's essentially a volume with height, width, and a time dimension of 1. For a video, those frames stack together into a true 3D volume, with height, width, and time all represented natively. Then it applies 3D convolutions, meaning the convolutional kernel slides through all three dimensions simultaneously. This gives the model native spatiotemporal understanding. It can process an image at 896 pixels of resolution, handles short videos at 128 frames, and even digest long videos with up to 2048 frames. And the key advantage here is that everything runs through a single unified pipeline, no separate processing for images versus video. Let's talk about how Kimi 2.5 goes from a strong, pre-trained model to a state-of-the-art powerhouse. The post-training recipe follows a two-stage pipeline. First comes supervised fine-tuning, or SFT. Think of SFT as teaching the model how to properly format its responses and follow instructions. It's trained on high-quality, curated data to learn the right output structure. But here's the critical insight. SFT alone only gets you so far. It teaches format, but not deep reasoning. That's where the second stage comes in, reinforcement learning. RL takes over and pushes the model's reasoning quality to a much higher level. During RL, the model explores solutions beyond what's in the training data, gets rewarded for good reasoning, and learns to think more deeply. You can actually watch the quality progression go from a pre-trained baseline through SFT, where it gets properly formatted, and then through RL, where the actual reasoning ability jumps dramatically. SFT teaches the model how to respond. RL teaches it how well to reason. Now, the RL in Kimi K2.5 isn't your standard reinforcement learning. They made two crucial innovations that solve major problems in the field. The first is token-level clipping. In traditional approaches, you calculate one clip ratio for the entire output sequence. The problem? Every token in the response gets the same coarse adjustment. This collapses response diversity and makes the model's outputs predictable and boring. Kimi K2.5 instead applies clipping at the individual token level. Each token gets its own fine-grained adjustment. Some tokens might need a big update, others might be fine as they are. This granular control preserves the diversity of responses while still optimizing quality. The second innovation is the Generative Reward Model, or GRM. Instead of using a simple scalar score to judge responses, the GRM actually generates a detailed written critique. It reads the full model response and produces nuanced feedback explaining what was good, what was wrong, and why. This is far more informative than just getting a number between 0 and 1. Together, token-level clipping and GRM solve one of the biggest headaches in RL training: reward hacking. That's when a model learns to game the reward signal rather than actually improving. With per-token precision and rich feedback, there's no shortcut to exploit. Here's where things get really exciting. Vision RL is the central innovation of the Kimi K2.5 paper. Instead of only using supervised learning to teach the model about images, they applied reinforcement learning directly to visual tasks. Here's how it works. The model sees an image, like a chart or a diagram. It thinks about what it's seeing, generates a response, and then gets a reward signal. Correct answer? Positive reward. Wrong answer? Penalty. Over millions of iterations, the model gets dramatically better at interpreting visual information. But here's the surprise that makes this research truly groundbreaking. When they trained the model on vision tasks with RL, the text reasoning performance also improved. Let me repeat that. Training on images made the model better at text-only math problems. The vision performance jumped significantly, which you'd expect, but the text performance bars also went up, and that was unexpected. This phenomenon, called cross-modal transfer, suggests that Vision RL teaches the model deeper reasoning skills, things like spatial understanding, precise counting, and structured analysis that benefit text reasoning too. This is the key discovery of the entire paper. Let's dig deeper into this cross-modal transfer phenomenon because it's truly remarkable. Think of it like two hemispheres of a brain. The vision side gets trained with reinforcement learning on image tasks. You'd expect only the vision side to improve. But what actually happens is that glowing pathways form between the two hemispheres. Skills learned from visual training transfer over to the text side. So what skills are actually transferring? Three main ones. First, spatial reasoning. When the model learns to understand layouts, positions, and relationships in images, that same ability helps it reason about spatial concepts in text. Second, precise counting. Vision tasks require exact quantification, counting objects, measuring areas, tracking items. This precision carries over to mathematical reasoning. Third, analytical thinking. The structured problem decomposition needed for visual analysis directly improves how the model breaks down text-based problems. The benchmark numbers confirm this. AI ME 2025 math scores hit state-of-the-art. GPQA, graduate-level QA, reaches 74.9%, and HMTT competition math hits 79.2%. All of these are text-only benchmarks that improved because of vision training. It's like training one hand, making the other hand stronger. Neural cross-training at work. Another smart design choice in Kimi K2.5 is the thinking toggle. Not every question needs deep reasoning. If someone asks, "What's the capital of France?" you don't need the model to spend 50,000 tokens thinking about it. So Kimi K2.5 has two modes. Quick mode gives you fast, direct answers with minimal token usage, perfect for straightforward questions and factual recall. Then there's thinking mode, where the model engages in extended chain-of-thought reasoning. It analyzes the problem, decomposes it into parts, solves each piece, and verifies the answer. This mode can use up to 96,000 tokens for really hard problems like Math Olympiad questions. But here's the clever part. They used something called token-efficient RL to help the model learn when to think long versus when to think short. Instead of always burning the maximum token budget, the model optimizes for quality per token spent. It learns to find the sweet spot where you get the best answer without wasting computation. Think of it like a car with both sport mode and eco mode. You wouldn't floor it on a straight highway, and you wouldn't cruise in first gear on a mountain pass. The model learns to pick the right gear for each problem. Now let's talk about one of the most practical innovations in the paper, Agent Swarm. The idea is beautifully simple. Instead of having one agent struggle through a complex task alone, you have an orchestrator agent that spawns multiple sub-agents, each working in parallel. The orchestrator sits at the top and creates specialized sub-agents using a tool called Create Sub-Agent. Each sub-agent gets its own custom system prompt and set of tools. One might be a search agent with web search capabilities, another is a browser agent that can navigate websites, there's a code agent for executing code, a document agent for analyzing files, and task-specific agents for specialized work. Once spawned, the orchestrator uses assign task to dispatch work to each sub-agent, and here's the key, they all work concurrently. While one agent is searching the web, another is browsing a page, and a third is running code, all at the same time. When they're done, results flow back up to the orchestrator, which synthesizes everything into a coherent final response. This is built on what they call the PARL framework, Parallel Agent RL, where the entire multi-agent system is trained end-to-end with reinforcement learning. To really show what Agent Swarm can do, the paper includes a jaw-dropping demo. They fed it 24 hours of continuous Black Myth Wukong gameplay. That's 40 gigabytes of video across 32 separate files. The main orchestrator agent looks at this massive task and makes a smart decision. It spawns 32 sub-agents, one for each video file. All 32 agents start working in parallel, simultaneously. Each one extracts frames from its assigned video, performs temporal event analysis to understand what's happening over time, and identifies key moments like boss fights, level-ups, achievements, and dramatic scenes. As they work, results stream back to the main agent. Boss fight detected at timestamp 2 hours 34 minutes, level up at 5 hours 12 minutes, key story moment at 8 hours 45 minutes. The orchestrator then takes all these individual results and assembles them into a comprehensive interactive HTML showcase with chronological timelines and embedded video clips. The timeline fills out progressively, covering all 24 hours of footage. What would take a human days of watching and note-taking, the Agent Swarm handles through massive parallelization, like an army of scouts reporting back to a general who builds the complete map. Running many parallel agents means the context window fills up fast. Every sub-agent's results, every tool output, every conversation turn takes up tokens, and eventually you hit the limit. So how does Kimi K2.5 handle this? They developed two smart context management strategies. The first is called Hide Tool Result. When the context window hits a threshold, the system keeps only the most recent tool results and hides older ones. It's like a whiteboard where you strategically erase old notes to make room for new insights. The tool call structure is preserved, so the model still knows what happened, but the verbose output is hidden to save space. The second strategy is more aggressive, called Discard All. When the context is truly overwhelmed, the entire history gets truncated and the model starts fresh. This sounds drastic, but it's very effective for deep browsing tasks where you need to go many steps deep. The key difference from naive truncation is that these strategies are intentional and structured. Naive truncation might cut mid-thought and lose critical context. Smart management preserves key information while strategically removing what's no longer needed. They also set specific step limits depending on the task. 15 orchestrator steps for browse comp tasks, up to 100 steps for sub-agents using external APIs, and 50 steps for in-house sub-agents. Now let's look at the benchmark results, starting with text and math. This is where Kimi K2.5 really flexes. On AIME 2025, the Math Olympiad benchmark, Kimi K2.5 scores 86.7%, beating every other model on the board. On HMMT February, another competitive math benchmark, it hit 79.2%. On GPQA Diamond, which tests graduate-level scientific reasoning, it reaches 74.9%. Live Code Bench for competitive coding, 72.2%. And even on Long Bench version 2, testing long context understanding, it scores 62.2%. Every single one of these is a new state-of-the-art result. The evaluation methodology is rigorous too. For AIME and HMMT, they use average at 64 runs, meaning the model solves each problem 64 times and they take the average. And all thinking tasks use the full 96,000 token budget. This isn't cherry-picked performance. It's consistent, replicable dominance across every text reasoning benchmark that matters. Vision benchmarks are where Kimi K2.5's unique approach really shines. Instead of just looking at images and guessing, the model writes executable code to analyze them programmatically. Take maze solving as an example. The model uses binary segmentation to identify walls and paths, then runs BFS pathfinding to find the shortest route and overlays the solution. For a pie chart analysis task, it uses HSV color segmentation to separate regions, counts pixels in each area, and calculates precise percentages. For spot the difference puzzles, it generates pixel difference maps, applies contour detection, and highlights exactly where the differences are. This tool use approach goes way beyond pattern recognition into actual algorithmic problem solving, and the numbers back it up. On SWE-Bench, ranking the hardest zero-shot visual tasks, Kimi K2.5 scores 46.7%, dramatically outperforming the competition. MMU Pro for multimodal question answering hits 56.5%. Math Vista, combining math with visual understanding, reaches state-of-the-art. And for video understanding, both short videos at 1280 frames and long videos at 2048 frames, Kimi K2.5 sets new records across the board. On the coding and agent fronts, Kimi 2.5 delivers equally impressive results. For software engineering tasks on SWE-Bench verified, the model scores 75.6%, putting it at the top. It also achieves state-of-the-art on Terminal Bench and strong results on Live Code Bench. Now here's an interesting finding. The best coding performance actually comes from the non-thinking mode. Extended chain-of-thought reasoning doesn't always help with coding tasks. Sometimes a direct, focused response produces better code than overthinking it. On the agent side, the agent swarm architecture really proves its worth. On BrowseComp, the benchmark for complex browsing and information retrieval, the swarm approach outperforms the single-agent baseline by 17.8%. The model also achieves state-of-the-art on OpenUA and Web Arena for web interaction tasks. Speed-wise, the swarm runs 3 to 4.5 times faster than a single agent on complex tasks. Multiple agents working in parallel don't just get better results, they get them dramatically faster. It's the combination of parallel execution and RL-trained coordination that makes this system so effective. So let's step back and look at the big picture. Kimi K2.5 brings 3 fundamental innovations that push the entire field forward. First, Vision RL. The idea that you can use reinforcement learning to teach models not just how to read text, but how to truly understand visual information. Second, cross-modal transfer, the surprising discovery that training vision tasks makes text reasoning better. Skills transfer across modalities in ways nobody fully expected. And third, Agent Swarm, a parallel multi-agent architecture that makes complex real-world tasks 3 to 4.5 times faster, while also improving quality. The benchmark numbers speak for themselves. 86.7% on AIME for math, 75.6% on SWE-Bench for coding, 46.7% on SWE-Bench for vision, and a 17.8% jump on BrowseComp for agents. But there are still open questions. What are the scaling laws for Vision RL? How far can multi-agent coordination go before hitting coordination limits? And what happens when systems like this are deployed at massive scale in the real world? The future of AI is clearly multimodal, and Kimi K2.5 is showing us what that future looks like. One model, every modality, every benchmark. If you found this breakdown helpful, please hit that like button and subscribe for more deep dives into the latest AI research. Thanks for watching, and I'll see you in the next one.